Hello friends, welcome to this new video on random process. This will be an introductory video which says what is meant by a random process, how can it be classified, and what are various kinds of it. Come on, we'll quickly move on into the video. First, we will see about signals. The signals, which are going to be a function of time, can be of two types. They can either be deterministic in nature or they can be random in nature. So if we are able to define a mathematical function, give an input to it, and then we are able to get a definite output out of it, then you call it to be a deterministic signal. But if there are going to be elements of uncertainty, we will not be able to positively determine the outcome of the final value exactly at a particular point of time. So in this case, the signal will be termed as a random signal. So deterministic one are going to be finite and we will be able to say this is going to be an output. Randomness keeps us guessing this can be so or not be so and so on. It varies with respect to time. Now, how to define the process of a random process? Normally, we have seen about random variables. So, whenever we are doing a random experiment, we have outcomes out of it. This random outcomes, if we are able to associate along with a time function, then they become a random process. So finally, what we get out of them will be a function which is going to be time dependent in nature. So what we are going to do over here is the random variables which we have already seen in our previous sessions, we are going to associate it with a time function, and hence the process is going to be termed as random process. Hence, what we have over here is a random variable, a time parameter, and a state or an condition set S. So we have X, the random variable, the time parameter T, and the experiment's outcome, which are termed as S. So this X, T, S all put together will now become a random process. This is what we are going to see in detail in this video. Hence, we have a random variable capital X and a time parameter denoted by capital T and a set of all sample space elements denoted by S. Hence, this random process will be denoted as a function of elements from your sample space S and the time parameters T. This three together now forms our random process, which is denoted by x of S, T. S coming from the set of states or sample spaces and T coming from my time parameter. Now, what is meant by a random process? It's a collection of the random variable x of S, T that are functions of a real variable, namely time t, where S belongs to capital S and T belongs to capital T. S is our sample space and T is the time parameter set. Now, depending upon the inputs, we can classify them further as if both my S and T are going to be fixed, this is not going to change either with respect to my sample space or with respect to time, and hence it is going to be a mere number. Now, when this T is fixed, but this S is going to change. T is fixed and hence only the quantity that changes is my S. So now over here in my x of S, T, it becomes independent of this T and hence it becomes a function of S alone. And we know that this is nothing but our random variable. And if now S is going to be fixed and you have x to be a function of time alone, in which case this is going to be a single time function. If both S is also varying and T is also varying, then the collection x of S, T is a collection of random variables that are going to be time functions. This collection will now further be referred as random process. How can we classify this random process? We know that we have two components. One is going to be the sample space S, the other one is going to be my time parameter T. And I know that this S can either be discrete in nature or it can be continuous in nature. Discrete meaning it is going to be summed up, and continuous nature it is going to be integrable. Similar pattern, my T can also be discrete in nature or it can be continuous in nature. One which is summable, the other one which is integrable. Now when I take a combination of all these four together, now T being discrete, S being discrete, T being discrete, S being discrete, then you call it as discrete random sequence. When T is continuous and S is discrete, S is discrete and T is going to be continuous, then you call it as a discrete random process. Next, if T is discrete, S is continuous, you call it as a continuous random sequence. And if both of them are going to be continuous, you call it as continuum random process. Now moving on, what are the different types of random process? And how do we define stationarity? Can we say a random process is going to be stationary? How can we define it? A stationary process is one where all its statistical properties remain constant over time. What do we mean by statistical properties? Properties like mean, variance, standard deviation, all these quantities are going to remain constant with respect to time. Then you call the process to be a stationary process. But if these quantities change over time, then the process is termed as an evolutionary process. Next, what are the conditions for stationarity? So I now say a process is going to be stationary if it remains constant over time. Now, what are going to be the key conditions for it? The first condition for stationarity is that the constant value of expected value. What do we mean by the expected value? Expected value of x is going to be nothing but our mean. So I know that mean is going to be the expected value of the random process, in which case if it is a process, it becomes a function of t. So mean must be a constant. So mean has to be a constant. So this is going to be my condition number one. Second condition, the spread of the process is uniform over time, which means you have a constant variance. So condition number two now becomes variance of the process x of t is going to be a constant. So if my mean is a constant and variance is a constant, then you call the random process to be stationary in nature. So for stationarity, the two conditions which we'll be checking on is going to be mean is a constant and variance is a constant. Now, what is meant by first order stationary? First order stationary process is one where the first time translation doesn't change with respect to time. So it does not change with respect to shifting time origin. The random variable x1 is as such. If t1 is shifting to t1 plus h, for h is going to be a positive value. That is, you notice a shift in time origin. But it does not change. So the first value and the second value are the same. It is equal. And in which case it does not change, then you call it to be first order stationary process. This says that it means it is independent of time, and hence for a first order stationary process, the condition will be mean, which is expected value of x of t, is a constant. Now moving on to second order stationary process. If f of x1, x2, t1, t2 is the same as f of x1, x2, t1 plus h and t2 plus h for h positive, then you call the process to be second order stationary process. This implies that invariance under translation of time. What do you mean by translation of time? When you consider a difference in time t1, difference t2, and it is denoted by the script called as tau. We will be using this variable continuously now over here. So what does tau stand for? Tau stands for t1 difference t2, time difference between any two time parameter. If it is going to be invariant, so it doesn't change, then you call it to be second order stationary process. Now this is first order, this is second order, and so on. I can move on to nth order, in which case you call it to be strong sense stationary process or strict sense stationary process. A random process is called triple S if all its finite dimensional distributions are invariant under translation of time parameter. So T1, T2 up to Tn are all the same as T1 plus H, T2 plus H up to Tn plus H. Then you call it to be a strict sense stationary process. Now we move on to the next important definition called as autocorrelation of the process. What is meant by autocorrelation? Now, if we are going to have two members x of T1 and x of T2 of the process and consider that product and then take the expected values to it, then the outcome of it is referred as the autocorrelation. That is, we have x of T1 to be the first member and x of T2 to be the second member of your process x of T. Consider the product between them and then take the expected value of them. The output is referred as R of T1 T2 or Rxx of T1 T2 or simply Rx of T1 T2. So the process goes like this. So you select two values for the process, say T1, T2. Next, you compute the product between them. So x of T1 product x of T2. Next, you compute the expected value of them. Expected value of x of T1 product x of T2. And now you analyze this random process. So the outcome of it is Rxx of T1, T2. So this is how the cycle of the autocorrelation works. Moving on next, wide sense stationary process. A random process with finite first and second order moments is called to be a wide sense stationary process if its mean is a constant and autocorrelation depends only on the time difference tau. So there are going to be two conditions to be satisfied by a WSS. What are they? Mean is a constant and autocorrelation must be a function of tau. So this tau is nothing but a function of T1 difference T2. So this is my T1, this is my T2. Finally, the output must be a T1 difference T2. And next, moving on, we have joint WSS in which we have two processes, one x of t and the other one y of t, and they are going to be joint WSS if x of t is separately a WSS, y of t is separately a WSS, and the cross correlation xy. So you take the first member from the random process x of t, the second member from the random process y of t, compute the product between them, and then take the expectation of it. And if this is going to be a function of tau, then you call it to be a joint WSS. So this has to satisfy two property. E of x of t is going to be a constant. The second one, autocorrelation Rxx must be a function of tau. This has to again satisfy two conditions, namely E of y of t is going to be a constant and Ry must be a function of tau. Autocorrelation of y must be a function of tau. And then finally, the joint cross correlation between x and y must also be a function of tau. If all these five conditions are satisfied, then you call the process to be a joint WSS. I hope this introductory part is clear for you people. In the second video, we will move on to apply all these concepts to define problems and solve them easily and get a solution for them. Thank you.